Hello, friends. We need to begin looking at lecture number 4, where we will concentrate to look at looking at the special continuous distributions that include the exponential distribution and the normal distribution. So we start with the exponential distribution. That's our first. And determining the amount of time that passes until the next event occurs. So basically, you are examining how much time passes before one occurrence occurs. So examples would include things such as the length of time between emergencies, arrival at the hospital, the amount of time between the breakdowns of manufacturing equipment, the time required to load a truck, and the time between arrivals at a car park. Basically, what you're trying to do is to examine how much time passes, okay, until the next event occurs. So that's all what you're trying to do in exponential probability distribution. So you will understand that a continuous random variable, therefore, in the exponential probability distribution shall be defined as the f of x equal to 1 over mu e function to the power x over mu. Okay, that is for all. It is for all x variables that are greater or equal to what? To 0. So this is basically just the definition of the exponential function. So you will understand that you're given a function like this one that speaks, that says the function is defined as f of x should be equal to 1 over mu to the power negative x over what? Over mu. That is for all x variables that are greater or equal to what? To 0. So that's just basically the definition, and the 0 otherwise. So for all the values of x that are greater than 0, the function is 1 over mu to the power negative. Okay. So all what you need to concentrate upon now is nothing but this thing that I want just to give you. How do we make some simple derivations so that we can reach at the formula? So this is how you do the thing. We will start with example that says, can we suppose that the lifetime of an electric component follows an exponential? An electric component follows an exponential distribution with lambda that is equal to 0.1, and for the lifetime of the time, the lifetime is between, let's say, 5 hours and what? And 15 hours. So basically, when you look at the time has got a range, okay? There is a time period that passes from 5 hours then 5 hours shall be called our lower limit in terms of the time. So that's basically all what you need to know. You need to know which one is the upper limit, which one is the lower limit in terms of timing. So these are just basically simple derivations that are there now. So you are given that the random variable x, which is the life component, the lifetime of a component, follows exponential function, and our lambda has been given to what? Our lambda is 0.1. And then the time period from 5 to what? 15 hours. So here is what you do from here. So all what you're trying to do is to understand what lambda is. So is basically equal to 1 over mu. In our formula that we just had, our formula was saying 1 over mu e function to the power negative x over what? Over mu, 1 over mu. So we can break down the 1 over mu, this one over mu as lambda. Okay? This is as lambda. So you have lambda e function raised to the power. Again, here we can break this as 1 over mu. The exponent shall be 1 over mu times what? X over 1. We know once we multiply these, we get x over mu. So we can know that 1 over mu is basically what? Lambda, okay, times x, which will be lambda x. And that's why we can rewrite this as lambda e to the power negative what? Lambda x. So this is just the related version thereof. You integrate the function, you end up with something like this. So when you're done integrating, okay, when you're done doing your integrals, you should be able to end with the exponential function or the expression negative e to the power lambda, negative lambda x, okay, plus e the power negative what? Lambda x. Now, what you should understand is that let's say the lower limit, okay? Shall we just say that our lower limit is a, then our upper limit in terms of time is b, right? Our lower limit is a, our upper limit is b. So if that is the case, then this x here, we will rewrite it as what? Let me use a blue marker. We'll rewrite it as a, which means that the one that has got a positive number should always be the lower limit, where if I and we know that we can actually rewrite this, okay? Rewrite this expression as a to the power negative x negative lambda a, which is our lower limit, minus e to the power negative lambda upper limit b in terms of right, was just saying that we understand 5 is our lower limit, and then our upper limit shall be basically our upper limit shall be 15. So given our formula now, our formula for the range, as long in terms you do, you just say e to the power negative lambda c e to the power negative lambda the lambda b be the upper limit. This is where the time is what is a range. We use this when the time is actually expressed in terms of a range. Okay, so let's say for this one where the time is 15 and 5 and 15, so you can rewrite it as e, okay, e to the power negative, our lambda has been given as what? 0.1 in the question, plus, oh sorry, minus, minus this side, minus e to the power negative 0.1 lambda times our b is 15, then here this is multiplied by our lower limit, which once you do the computation, the e function is coming from the calculator. You should be able to get the solution 0.3834. Just say e to the power negative 0.1 times 5. You write the answer. The e function is just some number that is on your calculator, approximated to be number that is ongoing, but 24 decimal places, it is basically this number. That's the number that you put on E. That's the E number. So E raised to the power negative 0.1 times 5, and you write the answer. Again, you say minus E function to the power negative 1 times 15, then you basically get the solution. So you usually use this whenever the time is expressed in terms of a range. It's a range of time. For example, what is the probability that it takes between 10 to 20 minutes moving from the main campus to Graduate School of Business, GSB? So it's a range of time between 10 to 20 minutes. Obviously, 10 will be the lower limit and the 20 will be the upper limit. You just put into your, you substitute into your formula. A, let's say this is lambda, okay, lambda A, lower limit, minus E, the power, and negative lambda B, the upper limit. Just compute like that. Sometimes you might not be given lambda as lambda. You can just be given mu, right? Mu. Mu. But understand that 1 over mu is always equal to what? Lambda. That's the basic thing to understand. Now, that's all what you just need. What if now the time is expressed in terms of, let's say, probability that the x variable will be greater than, let's say, b in terms of time now. This b is representing some time. Question like, what is the probability that it will take you more than 10 minutes or greater than 10 minutes? About more than 10 minutes, all you need to write is your formula shall be e the power negative lambda b, just like that. That will be your formula for greater than. Okay, so just compute like that. This basically will give you greater than that, specifically greater than that. Okay, so it will just e negative lambda b. No lambda you're given, then you put the value that is given. If it's 10 minutes, you put it 10 here, and you just compute it, you have the probability. What if now you are asking about less? Let's say, what's the probability that it will take you less than, let's say, less than 20 minutes moving from Onza, from the School of Education to the School of Veterinary Medicine? So what's the probability that x shall be less than what? Let's call this one now A to represent some, this A is representing some time. In this case, let's say less than 10 minutes. So it will be probability that x is less than what? 10. How do you find this one? This one is basically expressed as this. Let me use a red marker. It would be basically 1 minus then we put A, just that value. So this is for less. If we say, what is the probability that it will take you less than 10 minutes moving from the School of Education to the School of Veterinary Medicine? So just say 1 minus E function, you already know the E function, to the power negative lambda over A. I already said that sometimes you cannot be given lambda, but if you're given mu, just understand that you divide just 1 to 1, say 1 over mu, that should always automatically give you lambda. So there is nothing difficult, you just do the computation, just know these two formulae, and then you'll be able to answer any question under exponential that asks about the time that elapses. If it gives you the time that is less than something, you record like that. Time that is greater than something, you record just like that. And that is in between, if the time is expressed in terms of the range, you say E to the power negative lambda. Let's say A represent the lower limit minus E to the power B, okay, negative lambda B to represent B, represent the upper limit. That's for the range. So that's all what you do actually under exponential function. Any question? Okay, now that we don't have any question, we can fast forward move to the normal distribution, okay? The standard normal distribution. Yes, that the probabilities should always be between 0 and 1. All the answers for probabilities shall be between 0 and 1. But what about when you're given some very big numbers? Like, what is the probability that when you buy a car, it will be able to move 15,000, like 15,000 mileage? Okay, before the car is disposed of or is useless, right? So when you look at the figures of 15,000, what's the probability that to be the car will just spend less than let's say to spend less than 40,000 mileage, or more than 40,000 mileage, or it will spend exactly 40,000 mileage? When you look at these figures, these are very, very big numbers. But what you need is basically the skill to reduce these huge, huge numbers into very, very small numbers. Those very small numbers into what is known as a z-score, okay? A very small number. That number is what will lead you to the probability that shall always be between 0 and 1. So how do you convert those huge numbers to small numbers of equivalence? You compute what is known as a z-score. A z-score is given as x value minus the mu over the given the standard deviation and given that x variable or that is under concern, then you can actually compute this z value or the z-score. The idea behind computing the z-score is that you should get some number very small, which can easily help you to go to the probability that is between 0 and 1. Examples do better. So now, let's make an assumption that the z variable has already been calculated, okay? If the z variable has already been, begin by calculating, not just has already been calculated. But before we talk about that, may I just quickly highlight the properties of the standard normal distribution curve. Number one, it is bell-shaped. To be bell-shaped, it simply means it's like this, right? Number two, it is symmetric about the mean. So that is to say, mu is always equal to 0. To be symmetric, it simply means the right side, this side is always equal to the other side, the left side. That's what it means when you say it is symmetric. And the area from negative a to 0 is the same area from to a. So let's say this is 0 at the center. we have some value here. Let's call this is a z value, z critic. Even this side we have negative z critic. So from the 0 here going this side, it is equal z moving from 0 going this. Okay, so under the normal probability distribution, so this is just basically the same. So you find that we usually use area and and probability are the same things. But at the same time now, we can move forward and try to look at one good example. Okay, one good example from here. But given that an engineer at Toyota, let's say an engineer at Toyota has built radio tire and have estimated that the mean tire mileage is actually having the mean of, or the mu of 36,500 miles, and then the standard deviation thereof is 5,000. It's kind of assumption. Okay, so the question is, what is the probability that the tire mileage exceeds 40,000? Okay, so that's the question. What's the probability that the tire mileage will exceed 40,000? Given that on average, most all the tires just spend about 36. But what's the question? The question is now, what's the probability that this tire will be able to spend more than 40,000 mileage? So when you look at these numbers, these are really huge numbers. So how do you handle these huge numbers? You need to convert them into a small number, very small figure, so that that smaller figure is able to lead you to the table, which we call the standard normal distribution table, where you can get the areas that are already computed there. Okay, so let's or score. So a z-score is given as the x bar minus the mu over standard deviation. So our x in this case is 40,000. So let's write 40,000 minus 36,500 all over the standard deviation of 5,000. That should be equal to 0.70. So we have calculated our z-score as what? 0.70. We are 70 is an answer, but instead it's just some value that can easily lead you to what? To the correct solution. Is some value that can easily lead you to the answer. So this is basically what we are trying to do. Okay, the z-score is basically leading you to what? To the answer. The answer. So how do you go to the answer now? You use this z value. This z value 0.0. So it will guide you to the table. So from this diagram that I'm just trying to draw here, so I can easily visualize, you know that the z values are always in this here, and there is a 0 here at the center. Inside, if we want, we can even put a negative 0.70. Okay, just like that. So we are going to go, before we go to the table, to select the answers, I want you to understand this. I've already highlighted that the total area this side is 0.5 going to the right, and similarly to the left is 0.5. One thing that is very crucial and that you need to understand is that if the question is asking that what is the probability that Z is equal to 0.70, you know that 0.70 is 40,000, right? We have converted the 40,000 into its equivalence. The Z score that is equivalent to that, which is 0.70. So expressed in 2 decimal places. That area, if we are asking that, what is the probability that the tire mileage will be exactly 40,000 or will be equal to 40,000? That is the question, same question as what's the probability that Z or the Z score, the Z value 0.70. That area, in short, that you're looking for is just the area from 0 here up to 0.7. This is the area that corresponds to Z is equal to what? 0.70. But what if you're asking that Z is greater than 70.0? It's greater than 0.70. So the area, in terms of your visualization, this is how it will be. You know where 0.70 is here, that's where you put the Z value. Have 0 here, you have negative 0.70. So you're asking to find the area that is greater than 0.70. It is basically this area that is shaded after 0.0. This is the area that is greater than 0.70. 40,000, okay? This is the probability. This is where you can get the probability that this area is equivalent to the probability that the tire mileage will spend more than 40,000. But what if that's about greater? So whenever in this question we are asking about the question, what is the probability that it will exceed 40,000, okay, the tire mileage? So it means that we are looking for this area which is greater than the Z value, which is after this Z value, right? But what if you're asking about less, okay, less the Z value? Let's say the Z value is less than 0.70. Obviously, it is all this area that is less than from negative. I understand that this is 0.5, okay, and going this side is 0.5. So this is just the basic thing that you just need to understand before you can go to our table. So in short, this time around, we are looking for the area that is Z equal to 0, where the Z is equal to 0.70. Let's go straight now to the table and locate that area, okay? Locate that area. If you are using this area, this table, are you able to see this table? This is the table that I'm using now. Standard distribution table. Now, one thing that you should understand before you use the table is to see how the table is defined in terms of the way how it is shaded. This table is shaded in such a way that it gives all the area from the Z value going to the what? The left. Okay. So all these areas that we have in this case, our Z value is 0.70. Meanwhile, in between here, there's 0. Okay. So it is all this area that is shaded. So what is not just shaded is this area after the 0.70, and it is basically the area that we are looking for, or the probability that we are looking for, okay? The probability that is after 0.70. How do we find that? If this table that we are using just gives us the area before, just before the Z score here, all this going to the left. So we can go where there is 0.7 and 0.00. You know, when you add all these, you find 0.70. If you're given a number like 2.5, be 0.04. That will still give you 2.54. Similarly, if you're given a number 2.31, you can break down this as 2.3, and 0.01. You add this, still get 2.31. So basically, that's how you have to understand this thing, that the z value is always expressed in two decimal places. So we go where there is 0.70 and where they meet with the 0.00. It is this area. So the area that we find is 0.7580. This is the area, okay? This is the area where this is 0.7 meets with the 0.00. They meet on this area. Now we know that this area just represents this area which is shaded, okay? It just represents the area that is equivalent to this. But as we are not interested in that area, as we are interested in the area that is after this value, which is not shaded. Now, since we understand that the total area under this curve is what? Is 1. We can just say 1 minus 0.7580 so that we can actually get the what? Get the area that is after 0.70, and this will be 0.24 and 26. This is the probability, or this is the area that is after 0.7 is after the area that is 0.70 in this respect is equal to 40,000. So this is but what if the question is asking about the area that it is less than 40,000, meaning less than the z value, okay? Less than the z value. The z value is 0.70. The area that it is less than z value. It is basically the same area that we had found, 0.75880, because the table that we are using, it shows that the area that we find is always the area that is less than the z value going to the left. Okay, less than z value going to the left. Asking about the z value equal. The z value equal to what? The area is that the z is equal to 0.70, not less than. And I said that if they're asking about something equal, it means that they want this area from 0 here up to 0.70, all this shaded area. How can you find this shaded area? We know that the area that we found, 0.7580, it is all this area from 0.70 going to the left. And we know that after 0 here going to the left, it is 0.5. So to remain with this area, let me use blue marker. To remain with this area, obviously just have to subtract 0.5 from 0.7580. So you say 0.7580 minus 0.5. Once you subtract the area that is equal to the what? That is equal to 0.70. Okay, that is equal to 0.70. And in this case, our area is 0.2580. 0.2580 is the area that is equal to what? To 0.70, not greater than, because for greater than, it is this one that is after this. You get this by just basically subtracting this number from 1. Any question? Okay, cool. So we can actually, the example is where you're given 93 values. Okay, you have 93 values. So still you have for less than 93, greater than 93, and equal to 93. We still go direct to our table. Let's just go direct. Probability that z is equal to 93 or 0.93, and the Z is less than 0.93. I think this is just same as the example that we had. For what is less than, looking at our table already gives us the areas that are less than what? 0.93, that are less than the Z value, because it gives us all the areas going to the left. So we just go where there's, 0.93 can be broken down at 0.9 and 0.03. This still gives us 0.93. So we just go where 0.9 meet with 0.003. Okay, 0.9 meet with 0.03 from this step. Let's go where there is 0.9, 0.9 here, and 0.03 here. They meet on, the area is 0.82 and 3.38. This is the area where they meet. So this is the area that is equivalent to this diagram. Okay, 0.93. It is equal to this shaded part. So if you ask it that, what's the probability that Z is less than 0.93? It simply means you're giving this. But what if the question is asking about greater than 0.93? It means that they are asking for this area which is after 0.93, this area. Okay, how can you find this area if you already know this area as 0.8238? You simply say 1 minus 0.8238, because you know that the total area or the total probability is basically 1. So you say 1 minus 0.8238. That gives you the area that is equal to 0.1. So that is greater than what? The area that is greater than 0.93. This is the area that is after. The area that is less than, it is this one. We get it direct from the table. So I say 1 minus that area should give us the other part that we have not been given. But now the question is, what if we are asked to find the area now that is equal, not less, not greater, but equal to what? Where Z is now equal to 0.93. So we already know that from here on the center we have 0.93 is this one. So we are asking for the area that is equal to this one. This is the area that is equal to 0.93. So basically, what we can do, since we already know that this side, this area up to 0, from negative here up to 0 is 0.5, we can simply subtract it. We can just subtract 0.5 from this number and say 0.823638 minus 0.5. And what do we get? 0.8238 minus 0.5 should give us the area that is equal to 0.93. It's basically 0.3238. So this is the area where Z is equal to 0.93. We find it just like that. It is equivalent to this shaded area here that we have shaded, okay, that we have just shaded. So basically, this is how you do this in the question. Okay, so basically, this is all about this lecture 4. Yeah, and enjoy your studies.